It's kind of wild when you think about it. Take water. It can be a solid block of ice, right? A liquid you can drink, and then poof, it's an invisible gas we call steam. We're talking three completely different forms, but it's all the exact same stuff. It's one of the most common things on our planet, but it's hiding a pretty incredible secret. So, what's the deal? How is that even possible? How can one thing have three totally different personalities? Well, that's the puzzle we're going to solve together in this explainer. And trust me, the answer is awesome, and it'll totally change how you see, well, everything.
Okay, so to get to the bottom of this, we can't just stare at an ice cube. The secret isn't on the outside. We have to go inside. I mean, we've got to shrink ourselves down way, way down, past anything a microscope can see, into this hidden world of particles.
And that brings us to our first stop, the secret world of particles. Everything we're about to figure out all comes down to one single powerful idea. It's called the kinetic particle theory. And get this, it's actually super simple. All it says is that everything, and I mean everything, the screen you're looking at, the air you're breathing, even you, is made of tiny little particles. And here's the kicker. These particles are never, ever still. They're always moving, always jiggling around.
So think of it like this. This particle world has a few basic rules. Rule 1, everything's made of particles. Rule 2, they're always moving. And this is the important part, how they're arranged and how much freedom they have to move around is what makes a solid or a liquid a liquid. And that leads to the biggest rule of all. It all comes down to energy. The amount of energy these particles have is what decides everything.
Okay, so let's move on and see this in action. With those rules in our back pocket, let's take a closer look at the three states of matter and see what those crazy particles are actually doing. First up, solids. In a solid, the particles have pretty low energy, so they're packed together in this super tight, neat, orderly pattern, almost like soldiers standing in perfect formation. They're locked in place by really strong forces, so they can't wander off. But they're not totally still. They're just vibrating, buzzing on the spot. And that right there, that explains exactly why solids are, well, solid. Because all those particles are locked into that rigid grid, a solid has its own fixed shape and its own fixed volume. You can't just squash it easily. That solid structure is a direct result of its tiny, vibrating, tightly packed particle. Now let's start turning up the heat. Let's add some energy. In a liquid, the particles have just enough energy to break out of that rigid formation. They're still packed in pretty close, but now they can start to tumble and slide right past one another. The forces holding them are weaker now. Think less military parade and more crowded dance floor. And this whole sliding around thing, that's why liquids do what they do. Because the particles can move around, a liquid doesn't have its own shape. It just flows and takes the shape of whatever you poured into. But since the particles are still touching, a liquid still has a fixed volume. Okay, now let's crank the energy all the way to 11. In a gas, the particles have so much energy that they've totally broken free from each other. They're super far apart, just flying around like crazy at high speeds, bouncing off the walls and each other. It's basically a chaotic mosh pit of particles. And this total chaos is why gases are so wild. With all those particles sipping around so far apart, a gas has no fixed shape and no fixed volume. It'll just keep expanding to fill every single nook and cranny of any container you put it in. So here it is, a head-to-head comparison. You've got the orderly vibration of a solid, the sloshy dance of a liquid, and the high-speed mayhem of a gas. It really does all just boil down to how much energy the particles have, how they're arranged, and how they move. Okay, so that leads to the next big question, right? If it's all about energy, then what happens when we start adding it or taking it away? How does an ice cube actually become a puddle of water? Think of this diagram as our roadmap for changing states. When you add heat energy to a solid, its particles vibrate more and more violently until, bam, they break free and melt into a liquid. Keep adding heat and they'll start moving fast enough to escape completely, boiling off into a gas. And of course, it works in reverse. Take that energy away, cool it down, and gases condense into liquids, and liquids freeze back into solids. Now, this is where it gets really, really cool. See those flat parts on the graph? What's up with that? I mean, you're heating ice, the temperature goes up, but then right at 0 degrees as it's melting, the temperature just stops rising. It flatlines. You're still pumping in heat, so why isn't it getting hotter? Well, it's because that energy isn't making the particles move faster anymore. It's being used for one job and one job only, to break the forces holding them together in that solid structure. The same thing happens when it boils. It's an amazing peek at where the energy is actually going. All right, one quick thing we need to clear up because a lot of people get this mixed up. Boiling versus evaporation. They both turn liquids into gas, but they are not the same thing. Evaporation can happen at almost any temperature, and it only happens to particles right at the surface, like a puddle drying up on a cloudy day. Boiling, on the other hand, happens at one specific temperature, the boiling point, and it happens through the entire liquid. That's where you get those bubbles coming from the bottom of the pot. So we've seen how this one big idea explains the states of matter and how they change. But what's really amazing is how much else it explains. Let's look at a couple of other things you see every day. Ever wonder what's actually happening inside a balloon to keep it inflated? It's not magic. It's trillions and trillions of tiny gas particles inside, all constantly smacking against the inner walls of the balloon. That collective force from all those countless tiny collisions is what we call pressure. If you heat it up, the particles move faster, they hit the walls harder and more often, and the pressure goes up. Simple as that.
And how about this? You're in your room, and suddenly you smell someone baking cookies downstairs. How does that smell get to your nose? That's diffusion. Because all these particles are in constant random motion, they just naturally spread out. They move from an area where there's a lot of them to where there are fewer, just bumping and bouncing around until they're spread out evenly. This is just a perfect picture of diffusion. You've got this dark, heavy bromine gas just sitting in the bottom jar, but because its particles are always moving, it doesn't just stay put. You just watch. Over time, those particles spread out on their own, mixing with the air until the whole container is filled with a pale brown gas. Nobody's shaking it, nobody's stirring it, it just happens. Okay, for our final point, let's look at a classic experiment. Check this out. We've got a long glass tube. On one end, a cotton ball soaked in ammonia. On the other end, one soaked in hydrochloric acid. Now, these are both invisible gases, and they start to spread, or diffuse, down the tube towards each other. And right where they meet, they have a chemical reaction and form a solid white ring of ammonium chloride that you can actually see. But wait a second. Look closely. The ring isn't in the middle. It's way closer to the hydrochloric acid end. Now, if both gases are just moving around randomly, shouldn't they meet right in the center? So why is it all the way over there? What is that telling us? And here is the beautiful punchline. It's because lighter particles are faster. At the same temperature, little lightweight particles move way faster than big, heavy ones. The ammonia particles are much lighter than the hydrochloric acid particles, so they literally race down the tube, covering way more ground before they finally run into their slow, heavy counterparts. It's a perfect, visible proof that in the secret world of particles, size really does matter.